All right, let's talk solubility product constants today. We've been talking a lot about equilibrium if you've been following videos that I've posted in the last week or so. And I want to talk a little bit about KSP here. SP for solubility product. So we know that K, the expression for K is always going to be the same. It's going to be the concentration of the products over the concentration of the reactants, and raised to their respective coefficient powers. And solubility product constants will give us information about equilibrium that is created from solutions where a solid is being dissolved. So a solid is going from a solid to an aqueous form. So that kind of gives us information about those types of equilibria. And if we're thinking about equilibrium, then we know that the rate of the forward reaction is equal to the rate of the reverse reaction. That's what dynamic equilibrium is all about. These two things are happening at equal and opposite rates. If we're thinking about this with solubility, it's really that the rate of solution, meaning the rate of solid that is being dissolved into solution, is equal to the rate of dissolution. Meaning that the rate of the solid that's coming out of the solution is equal to the rate of the solid going into solution. So some of the particles are being dissolved and surrounded by water molecules, kind of in accordance with, that ionic theory of solutions. And then also these particles are coming back out and forming solids. They're precipitating out of the solution. So there's kind of both of these things happening simultaneously. And when the rates of those two opposing processes are equal, then we say that we're at equilibrium. So let's take this particular example. I like to do this demo when we first talk about solubility in class. Lead iodide has a beautiful yellow color to it. It's kind of Big Bird yellow for Sesame Street fans out there. So lead iodide is a fairly insoluble solid. It's actually one of the ones that we use as an example of something that precipitates out when you do those kind of metathesis exchange reactions where you end up forming a precipitate at the end. And you can do net ionic equations and all that good stuff. But realistically, even though it's a solid, there's still some of it that is dissociating. And so this process, how much of it dissociates, is a measure of its solubility. That's what the solubility product constant gives us, is a way to measure how soluble this solid is. We talk about things like solubility tables, and we give you general trends of which things are more soluble than others, and what is going to always dissolve in water, what is sometimes going to dissolve in water, and what is insoluble. So when you're talking solubility product constants, usually you're talking about fairly insoluble solids. And that means that when we're thinking about a K value for this, the KSP is going to be the concentration of the ions. So here's my lead and my iodide. I'm going to raise it to the second power here because I've got two of them. And normally we'd say it's the concentration of the products over the concentration of my reactants. But in this case, my reactant is a solid. So how can I talk about the concentration of a pure solid? Well, I can't. 100% of the solid is solid. So it's essentially over 1. So realistically, this KSP value is going to be related to how many ions we have in the solution. And so the magnitude of this number is going to tell me how well this thing dissolves. So KSP is really useful when you're asking questions like, well, how do I know if something is going to dissolve? Or how do I know how much is going to dissolve? Then you can go to the KSP value. All right, so let's look at another example. Let's do iron hydroxide. Most of the weak bases that are solids, solid, got ahead of myself here. Most of the weak bases that are solids are fairly insoluble in water. That's why they're weak, right? There's a relationship between the two. So this gives me my my iron. I know the charge on my iron is 3+ because I know hydroxide is -1 and there's 3 of those. So if I said, well, what is the expression for KSP for iron hydroxide? Then you would say, okay, well, KSP is equal to the concentration of my iron times the concentration of my hydroxide raised to the third power, right? And then I could look up that value. I could even calculate the solubility of these ions in solution, etc. Okay, so there's going to be a relationship then between solids that when they do split apart, they form some sort of species in the solution that is going to cause a change in pH, and we'll kind of get to that in later videos. But for the meantime, this number, as we're looking up the K values for these various solubilities, these are going to give us an indication of how well things dissolve. All right, so let's see how we can use this to do some problem solving here. So let's look at this problem. We have silver ions that can be precipitated out as silver chloride from used photofixing solutions. So this is kind of a cool fact. Old x-rays have silver in them, and actually some people have devised different ways to get the silver back out of old used x-ray film because the photofixing solution had some silver in it. So there's silver in old x-ray film that's just like laying around. A lot of people, especially in medical records and those kinds of things, will hang on to these x-rays for a very long time, and they're a good source of silver, which, oh, the irony. All right, so the solubility of silver chloride is 1.9 times 10 to the negative third grams per liter. And if we've talked about solubility before, it's usually a measure of density of particles, right? How many particles can I pack into solution? So that's a mass per unit volume. You could see that in grams per liter is usually the way we talk about solubility. When we're talking about density of particles, we usually talk about it in terms of grams per cubic centimeter, grams per milliliter. Either way, you can talk about it in any concentration units, but we tend to see either solubility in mass per volume or molar solubility in moles per volume. So using just this one piece of information, I can calculate the KSP. So let's first think about the reaction that we're looking at here. If we're thinking about silver chloride, here's silver chloride. We said it precipitated out, so this is my solid. Silver is a +1 cation, chloride is a -1, so it's a 1-to-1. Silver is one of those weird transition metals that only likes to be one charge in general. Most of the time, silver likes to be +1. All right, and when it dissolves, then I'm going to form that silver plus in solution and the chloride. Or you can think about this reaction in the reverse as well, because it's in equilibrium. You know, these species all exist in solution. It's just a matter of thinking about kind of which way are we thinking about it. Is it in solution and then it precipitates out, or is it or are we dissolving the solid into the solution? They kind of, you know, mean the same thing, but we're thinking about them from two different angles of the reaction. Okay, so if I look up my molar mass of silver chloride, then I find that it's 143.32 grams per mole. And this is going to be important because if I want to find the KSP, and I'm talking about equilibrium constants, then that should trigger the need for an icebox. I must have to make an icebox. But in order to make an icebox, I need to have molar concentrations. So right now I just have grams per liter, but if I know my molar mass, I can get to moles per liter. So let's do that. All right. Now, here's kind of a key step that is one that can be implied if you're kind of snappy with thinking about these things. But for every 1 mole of my silver chloride, I'm going to get 1 mole of my silver. And we could also think about this in the same way. I also get 1 mole of my chloride. So when I run the numbers through my dimensional analysis here, this is grams of silver chloride, moles of silver chloride, and I'll be left with an answer of moles of silver per liter, right? So it's a molarity of the concentration of my silver ions in solution. So when I run the numbers there, then I end up with 1.3 times 10 to the negative 5 moles of silver per 1 liter. Now again, that's useful because I'm going to rewrite this guy for ease of icebox viewing. So now this is a useful piece of information, because if I want to find the KSP for this process, then I make my icebox. I'm going to ignore my solid. So this part, so long as there's silver chloride solids present, it doesn't matter how much of it is in solution. So initially, right, I don't know how much I start off initially. I start off with nothing, I guess, essentially, right? It doesn't tell me. So before I start dissolving, there's none of these in here. The change that I see now is the solubility. That's kind of an interesting piece to all of this, is really I'm going to be increasing the concentration of this by the maximum solubility limit for each of these. And because it's 1-to-1, then it's going to be the same for each. So this change comes from the solubility, and the change comes from the solubility because solubility is a measure of how much solute I can pack into my solution. So that's given here, which gives me an equilibrium concentration like this. And again, if you get snappier with these kinds of things, then this is a little bit redundant, right? We know that this is the solubility, and we know how much this is we can get in there at equilibrium, so that kind of builds itself. But this is just relating it back to the ice boxes that we've seen before, because now if we set up our expression for KSP, that's going to be equal to the concentration of silver ions times the concentration of chloride ions, and that's going to be the 1.3 times 10 to the negative 5 squared, essentially. And when I plug in that value and round it to 2 sig figs, I end up with this. Okay, so what does that mean? What does that tell me physically about this? Well, this is a very small number, right? So if this is a very small number, then that means I don't have that many ions in solution. And we already kind of knew that because we knew what the solubility was. The solubility is also a small number, and it just kind of goes up exponentially from there when we start multiplying and raising them to their coefficient kind of exponents. So this is a small number. It means that silver chloride, if we kind of go back to the original reaction here, is a fairly insoluble solid. I would guess that if you saw a solubility table, it would say that silver chloride is insoluble in solution. It doesn't like to dissolve. If you have silver and chloride ions, they're going to want to precipitate out. And that's true. That's what you get from this number right here. But it's to varying degrees, and we can use those varying degrees of solubility to give us information about how things will come out of solution, how they go into solution, and these have a lot of interesting implications kind of moving forward.